Welcome. This is Computer Programming 1 from the University of Washington. I'm Martin Dickey. Today in Lecture 10, we'll be discussing loop development and program schemas. And I have a little surprise for you. I hope a little treat. Today will be the first lecture of the series in which I won't introduce any new syntax. We'll take what we already know about writing programs and about the C language and look at some of the problem-solving steps that will help us to write correct, effective programs. In doing this, we'll discuss some advice on how to get from the problem statement to working C code. We'll look at some fairly systematic ways to do loop design and development, since loop design is often one of the most tricky parts of getting a program right. And finally, we'll talk about the value of reusing code and reusing code patterns and look at one extended example in a number of flavors. That example will be the following one. Read daily rainfall amounts and print some interesting information about them. Picture this. At weather stations around the world, there often are not trained meteorologists. There may be hobbyists who keep a rain gauge in their garden and empty it once a day, making a note of what the rainfall is. My grandfather was one of those people and kept these records for many years in the towns where he lived. Once we have all this data collected and sent into the Central Weather Bureau, we can ask some interesting questions about it. We'll assume that the data being sent in is a number of readings that represent the daily rainfall for consecutive days. Here's an example of what this might look like. You see a series of numbers. They're all positive. They all look like doubles. The last one is a negative number. Now, since we know that rainfall can't be negative, we'll take this as a sentinel or a special value, as we discussed last time. We'll take this to mean there's no more data in the series. The weather meteorologist has no more data past the -1. If we have this kind of rainfall data, what could we do with it? Well, we might just print the data on a day-by-day basis, so we'd have a record of it. Or we could do some computations. We might say, how many days worth of data are there? How many days was it before my grandfather wasn't able to collect the data and put a -1 in the stream he sent to the Weather Bureau? Which day had the most rain and how much rain fell that day? Were there days that had no rainfall? How many such days were there? What was the average rainfall over the whole period, over part of the sum period? These are some of the questions that someone analyzing the data might want to know. We'll look at what might be similar about solving these problems in C and what might be different. Let's just do a couple of them in C first. Suppose our only job is to print the values that we have. In this case, we'll have to read in each value and print it out. Because this is a repetitive action and we know about loops now, we'll use a loop. Of course, we can set up a loop either using while or for, but since we don't know how many days there are and we're not counting the days, a while loop is probably better from a style point of view. In order to print the data, we first have to have its value. So before entering the while loop, you see a scanf, and then the loop body itself is a printf followed by a scanf. You should understand all the points of this program by now. There are no new logical concepts, and in fact, as I promised before, no new syntax in this example. Let's take a different example. Using the same data, let's answer the question, how many days worth of data are there? It's somewhat of a similar program, but we don't want to print any result until we're finished. At the very end, we see a printf statement that tells us how many days there were. To make this work, I'll need to have a loop that is counting, telling me how much input that is. You see that there in the while loop. The condition is rain greater than 0. If you compare this to the previous program, the condition is exactly the same. In other words, read until there's no more data. What we do inside the loop body is a little different. Now we're adding 1 to a counter and then reading in the next piece of data. To make this work, we'll have to have a variable called nDays declared and initialize it to 0. A similar program, but not identical to the previous one. Yet both of them have a very familiar feel about them. There are many structural aspects of the two programs that are the same. In both cases, we start by scanning in the first value and then entering a loop that includes as its last statement reading the next value. In both cases, the loop condition is exactly the same. Some of the details are different, but the overall structure seems to follow a common pattern. What we'll try to do is figure out what that pattern is, because if we have two examples or instances of it here, it's very likely we might be able to reuse the pattern for other applications as well. This leads to the idea of a program schema, which we'll define as a pattern of code to solve a general problem. This is sometimes also called a design pattern. Note that this is not a concept of the C language. This is a concept of program design, or what is sometimes called software engineering in general. Where do patterns come from? They come from experience. The more programs you write, the more ready you'll be to recognize that what you're trying to design for this program is similar to something you did yesterday or a week ago or a year ago. Then, if you're lucky, you can not only recognize the pattern, but find a way to reuse it, thus saving yourself time and thought processes. Here is a list of tips that you might keep in mind as you solve problems in the future. Look for the pattern. See if it matches something you've done already, or something you know someone else has done and has described or has left behind as an example. In addition, work the problem by hand to see what the solution is. Suppose the problem contains some elaborate computations. Instead of sitting down and trying to translate those into C, see if you can do them with pencil and paper. If you can't do them with pencil and paper, you're probably not ready to try translating them into C. Finally, after the code is written, try hand tracing it on simple test data. The simpler the better. For example, in our rainfall data, the simplest case would be that there's no data at all. Perhaps the rainkeeper was on Mount Kilimanjaro and was eaten by an elephant before any data had been collected. In this case, the only data that would reach the Weather Bureau would be a -1. Strangely enough, sometimes it's these very simple cases that give our programs the most difficult time. And so stopping and testing those cases first is often a very, very efficient way of finding problems in the code. Notice something else about this short list of tips. It doesn't directly address loops. These are tips you can apply to any kind of programming, any kind of algorithm, whether loops are involved or not. For the two cases we saw with the rainfall data, they can be given a common framework that we might call a schema. And let's give it a name. Let's call it Read Until Sentinel. Now what you see here looks at arm's length like a C program, but it really isn't. You look at the details, you see some things here that really won't compile. Instead, this is meant to be a general framework or outline for a C program. For a particular application, you would fill in these parts. Things like the yellow highlighted variable or declarations or initial. Sometimes we might call these placeholders. The word placeholder occurs in a number of contexts in this course. We used it for printf and scanf format descriptors. Here we simply mean something that will be filled in by actual programming, but in the schema is describing a general or a possible case. Placeholder variables will mean current data received from the input. In the rainfall examples, we will always have to go through the process of reading data into a variable and using that in the processing. Sentinel is a value that signals the end of the input. Now, declarations are additional variables that may be needed. In some applications, there may be no additional variables. In others, there may be very many. Initial refers to any statements that are needed to initialize variables. Exactly what the initial part of the program is would depend on the variables that are used as well as on the processing that is being done. The core of the program probably is what's inside the loop body. This is the main processing step, something that has to be done for each and every value in the data. And at the end of the application, some sort of result or calculation or action is generally taken. We'll refer to this by the placeholder of final. We specialize this schema just a little bit for our rainfall application, and we would get this. This is, again, not quite C code, although it's closer to it than the first version of the schema we saw. It's closer to C because we do have a variable declared for rain. We know we'll always need that. Declarations and initial are still left blank. We can fill in some of the details of the scanfs, however. And we also know what our condition is because we need to process every value in the data set. So rain greater than or equal to 0 will always be the condition. Let's think about what we can do regardless of the problem. The material inside the loop body is often the critical part of the program. So that might be the right place to start. Ask yourself what has to be done to process a single input value. Once you've done that, you might skip to the very end of the schema and ask yourself what has to be done when all of the data is processed. What should the result look like? When you have that, you can work backwards to get things that are written closer to the top of the program. For example, as you're thinking about the processing and about the final, you may discover that a variable is needed. That is the point in time to write that variable in the program in the place where it belongs. And I strongly advise you write a little comment on the variable as you do that to remind yourself of why you declared that variable and what its purpose is to be. Sometimes the last thing to think about is the initialization conditions. Once you know what the processing is going to be, you know what all the variables are, it may be very straightforward now to go back and to find the right initial conditions. You might have noticed that it seems like I'm writing the program inside out. When you look at a C program, it seems like any other document. It seems to have writing that starts at the top and continues down the page until you reach the bottom, or the bottom of many pages. Don't let that fool you into thinking that writing the program is the same linear top-to-bottom process. Writing the program, developing the algorithm, might work in a completely different way. It might work starting at the middle and working out. It might work by starting at the bottom and working up. Let's take this read until sentinel example for rainfall and solve a couple of problems with it. Now, just to keep the slides small, there are some boilerplate statements that I'm not going to show on the slides, but here they are for reference. We have a pound include and the boilerplate that goes with any main function. Within that is the loop schema, and that's the part that I'll reproduce and specialize for the examples that we'll see. Okay, job number 1, print the rainfall data. The same problem that we solved earlier, except this time I'll do it using the schema to help guide my algorithm development instead of some ad hoc method, which might be correct but is not as systematic. Recognize that there are 4 placeholders to be filled in eventually: the decals, declarations, initializations, the processing in the loop body, and the final. The core of this is the processing inside the loop body. And that's a very simple process. I want to print every value that must therefore be in the loop because that's the only place at which I have access to each value in the data stream as it's read in. So the printf goes there. Now let's take a look at that. The printf has to display something. What is that? Well, it's the same variable that I have in all the schemas, the variable that holds the value used by the scanf. Is there anything else I need? It doesn't seem like it for this example. So instead of requiring many statements and much head scratching in order to solve the problem, I've essentially reduced my solution to a single statement within the context of a previously understood framework. Let's try another one. Maybe not quite as simple. Here the question is, how many days were there with no rain at all? So it's a question of counting things. How many days are there going to be? It looks as though we don't care much about the actual values except whether there was rain or not, whether the amount of rainfall was 0 or not. Let's start again with the processing in the loop body. We want to count the number of days when there was no rain, so a counter that we add 1 to seems to be the right sort of thing, and we only want to add 1 if the rainfall is 0. That's a fairly straightforward conditional statement. We can code that using an if. Well, if we're going to write this, it implies there's a variable called n dry days. So I'd better go back now and put that in my declaration section. And while I'm at it, put a comment to remind myself what it is. Now, the comment shouldn't be the only form of documentation. The comment appears only once in the program, but the n dry days might appear several times, and so we should choose a name that's meaningful. Instead of an X or a Y, a name like n dry days would tell a reader what the programmer had in mind. Now, you might object at this point that an awful lot of the examples in my lecture slides have things like X or Y or N. It's an easy habit for programmers to fall into. It's certainly shorter to type, but in the long run it's not a good habit. I have the further excuse that the space on the video slides is limited, but if I were writing this program to read again myself in a month or a year, I would not use X's and N's. I would use descriptive names such as the one I've used here, n dry days. So next time you see an X in my slide, you might mentally substitute a name that makes more sense. That's what I would want to do. And that's what I would want you to do too if you were writing a program for me. Are we quite finished here? Well, not exactly. We know what processing we want to do at each iteration of the loop. What do we want to do when we're all done? Well, we want to say how many dry days there were. That information will already exist because we have the loop set up, so we need a simple printf statement. That seems to be all the processing and logic that we need. Now we just better double check to make sure the variables declared have proper initial values. To make this work, n dry days should be initialized, think a minute, and the correct initialization would be set it to 0. And so now we filled in this program using the existing schema to guide us. Should we do one more? Problem here is to find the largest daily rainfall during this period of time. Okay. Let's start with the processing itself. Now here, we have no idea which day might have had the largest rainfall. Okay. Might have been the first, it might have been the last. Okay. So let's keep a variable that holds the amount of rain that fell on the day with the largest rainfall. Okay. Then, once I have such a variable, every single day in my series, I can say, is the rainfall today more than the maximum rainfall I've found so far? Okay. If it is, then I want to change my max rain to today's value. If it's not, I don't want to. Finding a max like this turns out to be a fairly common problem in many, many programs, and you'll get lots of practice writing it. It's a good idea to learn this particular pattern almost by heart. In setting up the processing, I had to use a variable which I called max rain. Now I can go back up to my decl section and declare that needs to be a double, and a comment there helps me remember what it was for. When I'm all finished with the program, the answer I want to put is what was the maximum amount of rain. That will now be easy because I know that whatever was in max rain should have that maximum value. At least it seems that way. Okay. Anything else? Well, the initial value. Now, here we have to pause and think what a good value would be. And I'm going to propose this one, 0. Okay. Why? Because we'll never have a value less than that. So if it ever rains on a day and there's more rainfall than 0, then the first day that that happens will become the day of maximum rainfall. Okay. Seem to make sense? Logical step-by-step process. And although these three programs print quite different pieces of information at the end, we went through a very similar intellectual process to come up with them. Let's do just one more. Processing to find the average daily rainfall. Now this is a little more complicated because average involves two concepts ultimately. It involves taking the total and dividing by the count, how many things there are in a series. So as we go through the processing, we have to make sure that we're going to end up with both of those values so that in the end we can compute the one value, the average. Okay. So I have two assignment statements in my loop. One accumulates the rainfall, one accumulates the number of days in the series. Two variables were discovered, two variables are declared, and we have to find plausible initializations for them. Now that we have this, it should be easy to write the final. Okay. We'll printf. Well, what is the average? The mathematical definition, the total divided by the count. Okay. Nothing could be simpler. And you might write this program, you might test it, and it might seem fine, and you might turn it over to the client, and then you might get a call at 3 a.m. someday. My program just blew up. Well, what was the symptom? The machine crashed with a mysterious message called divide check. And you say, uh-oh, I never thought that would happen. Famous last words. Things you don't think will happen, do. There's only one place where division occurs in this program, and that's in the final. Total rain over n rain. Okay, back to your math knowledge. What happens when you divide by 0? Well, it's undefined in mathematics. But in a computer, it will tend to cause a fault. The hardware will not like being asked to divide by 0. And something bad is going to happen. How could you have a 0 there? Is that even possible? What would that mean in the real world of rainfall? Isn't there always some day in the series? The number of days is what we're dividing by. And the answer, you suddenly remember, is no. If the weatherkeeper was eaten by an elephant before the very first record was taken, the number of days in the series would be 0, and n rain would be 0. The first value read in would be the -1. The loop would not execute even once, and we still have 0 in n rain. It's easy to fix. We just need a conditional to check to see if n rain is greater than 0. Only do the division in that case. And otherwise, print some kind of informative message to say no data. Sometimes little conditions like that aren't thought through can be the downfall of great, big, complicated, otherwise wonderful programs. Loop design and program design is not always a top-to-bottom process. Sometimes taking things in the order process, init, final is useful, declarations as needed. But I don't want to give that as an absolute recipe either. You should remain flexible and adapt your thought process to the algorithm being designed. If you know a program schema, it can often be very helpful to look at another example of it or to adapt it to what you're using. It may save time and it may also save errors in thinking. If you use these general strategies, I think you may find your program development efforts much easier as you become familiar with more and more programming features and are asked to do more and more complex applications. Please join me for the next lecture in this series.